We're getting on to the commutative law here, which explains a little bit about something we've been doing with the longer expressions, but will also allow us to move terms around to make a little more sense when we're seeing these big, complicated expressions. The first version of this is that any terms joined by an AND can simply be moved about in the expression without it changing the output. Now that feels right, but let's prove it. The diagram on the left is for A and B, whilst the one on the right is for B not A. Many of you will take a look at these circuit diagrams and go, well, whilst the one on the right is for B and A. Many of you will take a look at these circuit diagrams and go, well, of course that makes sense. Swapping the order of the inputs makes no difference to the outputs. You're right, but let's prove it definitively with the truth table. Now that we have two controlled inputs in our truth table, we need to deal with all the possible options, and this increases the size to what we were used to originally. Let's start where both A and B are 0. Well, you'll see that both the expressions have two 0 values, so we'll have a 0 output. With only one 0 input and a 1 input, both of the AND gates will only output 0. Finally, with both inputs being set to 1, both AND gates output a 1. So yes, we've proved that both of these expressions are identical in terms of output, and therefore we can just swap between them. What this means in reality is that if we have a series of AND connected terms, we can change the order within that linked expression without changing the meaning of it. The commutative law can also apply to the OR gate, with us being able to move the terms around the OR symbols. Again, you can tell that's the case just from the fact that we're moving the position of the inputs when we look at the circuit diagram. The truth tables tell us the same story. Remember that an OR gate gives us a 1 output if either or both of the inputs are 1. Well, that means the order of them doesn't matter. So on both sides we're getting a 0 from two 0 inputs. Then when we have a single 1 input, we'll get 1 output. And also in the case where both inputs are 1. So again, identical. This means that if we see linked terms with an OR, we can move them around without changing the meaning of the expression. On the surface, this might not seem very useful. But moving terms around can help us identify where we can apply other rules and reveal to us things that would otherwise be more difficult to see. In action, let's start with something simple. This is just a jumble of terms all separated with OR. That means that E or C or A or B or D can just be reordered to anything you want. In fact, A or B or C or D or E reads a little bit better and means the same thing. In this case, it's a bit of a pointless task because it's not any simpler than before, and you'd be right to think so. But as we move through these, we'll see some examples where moving them around actually helps us simplify on a grander scale. But we won't be doing that with the next one. Let's look at the same thing but with ANDs. Again, we can just reorder the expression without changing the meaning. Whoop-dee-doo. Not very exciting yet, is it? Okay, now we're getting into something with a bit more meat on it. A and C or B or C and A or C. Let's start by identifying what's connected by ANDs and what's grouped with ORs. The commutative law means that we can move any of those sub-expressions, the yellow blobs, around as they're all linked with the ORs. A good strategy is to try and group like terms together. So let's move it around so that A and C or C and A are a little closer. At this point we can apply the commutative law to the AND expression C and A, so we can move it around and wow, we've got two lots of A and C. We've got a law for that. The idempotent law will tell us to remove the duplicates. So bye-bye little duplicate. Boom, smashed it. Now, we probably wouldn't have been able to even spot that we could apply the idempotent law without all that rearranging we were able to do thanks to the commutative law. That's it for this video. Don't forget to like, comment and subscribe to get more computer science content.